Hey, how's it going, guys? Happy Tuesday, and unless you spent a lot of the long weekend getting caught up on some old geometry videos, you haven't seen my face for a while, so it's good to see you again, and we're going to re-begin here now. Hey, we're up to the second to last section of Chapter 5. We're getting pretty close there with similarity. So what today's topic is going to be, this Tuesday, you're going to new lesson, more on triangle similarity, okay? Finding more shortcuts for triangle similarity. So far, we have one, right? We did this last section. We have the AA similarity postulate. You remember that one? We have one triangle, another triangle. They have two angles in one triangle, or congruent to two angles in another triangle. We would know that the two triangles would have to be similar to one another. That was an assumption. That was a postulate. So today we're getting two more. That's right. We're going to fill things out here. And very similarly to triangle congruency, where there are a whole bunch of ways to prove one triangle congruent to another triangle, there are a few different ways to prove that one triangle is similar to another triangle. But only three ways to really worry about here. Got the AA similarity postulate, and today we're gonna prove two more. So they're going to be theorems, right? We're gonna prove that if the AA similarity postulate is true, then a couple other things follow from that. We're gonna have another similarity theorem, and then another similarity theorem. And yes, we're gonna use letters like S and A in those, similar to triangle congruence postulates. So let's get on into it. Start with those two new shortcuts, which is really the main part of the lesson today. I'm going to talk about one thing that's going to help us actually prove that these shortcuts, right, beyond the AA similarity postulate, we're proving new ones today. I got something that's going to come up in the proofs. It's a little bit confusing, but I wanted to include in the proofs because it'll make proving of these new theorems a little bit easier here. And I just wanted to point this out to you. This was something that came up early in the book, but now we're going to apply it to similarity. And what this is that similarity is something called an equivalence relation, right? An equivalence relation. So not the most attractive thing, not the most interesting thing about this subject, geometry, is, what the heck an equivalence relation is. That really only came up in section 1.4. It comes up in the 9th grade textbook a bit, the white textbook that some 9th grade classes have, but a little bit more. But for equivalence relations, so in math, right, math is a lot of times you're describing relationships of things. One expression in algebra might be equal to another expression. One expression might be greater than another expression. In geometry, it's the same thing, right? One shape might be congruent to another shape. One side might be longer than another side. One angle might be shorter that are smaller than another angle. So there are a whole bunch of relationships between shapes, much as there are relationships between expressions or numbers in algebra. So wanted to point out to you that similarity is something special. It's a particular type of relationship that is an equivalence relationship. So it relates some sort of equivalence here. And in order to be an equivalence relation, you need to have three properties, right? Three properties must be true. And you know this because these three properties are also true for equality. Equality is also an equivalence relation. And congruency, right? Congruency here. We talked about that in section 1.4. You still do problem number 16 in section 1.4. It talks about equivalence relations here. But anyways, here are the three properties, right? These are three properties of similarity. And I'm pulling these straight from the properties of congruence and properties of equality. So you have seen these properties before. But just to prove it to you here, check it out here. This is the first criteria in order to be an equivalence relation in math, is that your relationship must hold in terms of reflexivity, okay? So similarity has the reflexive property. What do I mean by that? Well, reflexive property of equality is one number is equal to itself. Reflexive property of congruence, remember all your properties have to do with a particular relationship. Reflexive property of congruence is one shape is congruent to itself. So we know that, for instance, triangle ABC, well, it's just congruent to itself. Right, it's congruent to itself. Triangle ABC is the same thing as triangle ABC. But we can also extend that too to say that triangle ABC is similar to triangle ABC. So the reflexive property holds, right? Reflexive property holds. Okay, so some non-equivalence relationships, right, are, for instance, parallelity in geometry. Okay, so if you have a line, it can't be parallel to itself, right? Can't be parallel to itself. So reflexivity does not exist for parallelity. Doesn't exist for perpendicularness, right? Other things that shapes can relate to one another as. For numbers, right? A number can't be greater than itself. So the greater than relationship is not reflexive, right? Not reflexive, okay? But similarity is reflexive because a shape can be congruent to itself. Okay, if I want to prove that triangle ABC is similar to triangle ABC. Well, the freaking things are congruent to one another, so you get similarity for free. But I could say here, triangle ABC, well, it has a 30-degree angle, it has a 60-degree angle, and those 30-degree and 60-degree angles are congruent to, well, the 30-degree and 60-degree angles in triangle ABC here. So if you wanted to prove it, right, AA similarity, that's what would get you there. Okay, so similarity has the reflexive property of similarity. There's also the symmetric property of similarity. So this one here doesn't really come up in geometry too much, but it's part of the criteria of being an equivalence relation. Equality has it, congruency has it, and similarity likewise has it as well. So if a triangle is similar to another triangle, so here we have a triangle ABC, here we have A prime, B prime, C prime, and yeah, they're similar to each other through AA, right? I see that, they're similar to each other through AA. So if I knew a triangle is similar to another triangle, what can I say? What's symmetric, right? Symmetric. Well, we do symmetric with like parabolas have a line of symmetry, right? What does symmetric mean? It means looks the same thing on one side as it is on the other. So if triangle ABC is similar to triangle A prime, B prime, C prime, then, right, you should be able to conclude that that second triangle is congruent to the first triangle, or that second shape is congruent to, is similar to the first shape, okay? And vice versa, right? This is equal to that, just like that is equal to this. Or this shape is congruent to that shape, such as that shape is congruent to this shape, right? That kind of thing, it flip-flops. And then the same thing holds true for similarity here. If we knew that this figure is similar to that figure, then sure, we could say that figure is similar to that figure, okay? So again, symmetric is not true for certain relationships, right? That it's true for parallelity, it's true for perpendicularness. Can't really think of any geometry stuff it's not does not work with, but symmetric property doesn't go with inequalities, for instance, for a greater than, right? If a number is greater than another number, then that other number is not greater than the original number. Anyways, so just a little stuff here that there are certain things that we talk about in terms of equivalence relationship, and we'll use reflexive symmetric, and finally, similarity also gets another property, the transitive property, okay? So equivalence relations, again, hasn't come up since chapter 1 when we talked about congruency, about how congruency gets the reflexive property. It gets the symmetric property. And finally, it gets that pesky transitive property. The same thing is going to be true for similarity as well here, too. So if we check this one out here, if triangle ABC is similar to triangle A prime, B prime, C prime, so if one triangle is similar to another triangle, or one figure is similar to another figure, and that second figure is similar to a third figure, right? So here we have triangle A prime, B prime, C prime is similar to triangle A double prime. It's called A double prime right there. B double prime, C double prime. That's the one over here. Okay, so I know this here, ABC links to A prime, B prime, C prime. A prime, C prime, B prime, C prime links to that, right? So this is similar to that. That is similar to this other one over here. What can I deduce? Well, similarity, transitivity, is if one thing is equal to another thing, and that other thing is equal to yet another thing, then the first and third things must be equal to one another. That's similar to transitive property of equality, but transitive property congruence holds. And finally, this is a true statement right here, okay? If, as my premise here, I have this similar to that, and that similar to this other one right here, then this over here is similar to that other one over there, right? 1 similar to 2, 2 similar to 3, then we know that 1 and 3 we can deduce that 1 and 3 would have to be similar to each other through transitivity. They're both similar to the same thing. Similar to the same thing here, okay? So in order to save us time in our proofs today, one of these is going to come up. It might be the reflexive property of similarity, it might be the symmetric property of similarity, or it might be the transitive property of similarity here, okay? So one of the following is going to be used in the proof of today's first theorem, okay? Similarity is an equivalence relation, okay? We can use these properties. We can use reflexive property of similarity, symmetric property, or transitive property. And we're just gonna use that to make our lives easier in proving stuff today. And let's get to it. Similarity is an equivalence relation, so let's get this away and let's get finally into it now, because guys, you're getting your first shortcut today, right? Second one overall, we have the AA similarity postulate, and right now you're getting the SAS similarity theorem. Yes, the SSS similarity theorem. I was doing that for hobby there, I guess, the Macaulay Culkin. Anyways, SAS similarity theorem. So yes, so we have AA similarity postulate, right? We had to make that as an assumption. Now we have the SAS similarity theorem. So that means we're going to prove this, right? That's a whole setup here with that equivalence relation thing. Is I want to prove this with you guys. Hang out Tuesday. Prove some theorems with me. Let's do it. Okay? So this one reads here. So you're copying it down. As soon as you see these slides come up, right? So with the theorem, you're furious, taking copious notes, writing it down, because you're just listening to me talk on and on, or just looking at it in the freaking slide deck or in the lesson. That's not going to help you at all, right? You're writing it down, right? Kinesthetically, right? Getting it down in your notebooks. Do it. Put it down, okay? If an angle of one triangle is congruent to an angle of another triangle. Okay, so I guess we're getting this from SAS here. So the A stands for angle again, right? Corresponding angles. So if one angle of one triangle is congruent to an angle of another triangle, and the sides that include those two angles, well, I'll refresh you guys on what an included angle is. I think why not? It hasn't come up too much this semester. The sides including those two angles are blank, then the triangles are similar, okay? Well, hey, on the surface level, this looks very similar to the SAS congruency theorem. Doesn't it? No, that was postulate, right? Congruency postulate. So congruency would have been if an angle of one triangle is congruent to an angle of another triangle, and the sides, including those two angles, are congruent to one another, then the triangles would have to be congruent, right? They're an SAS congruency correspondence. This is a little different. This is an SAS similarity correspondence here, okay? So how do similar figures relate? Well, similar figures relate because their corresponding angles are congruent. Okay, corresponding angles are congruent. So what's that other word? Well, it has to do with the sides. Okay, similarity, all the angles are the same, but hey, they're different sizes. But then how do the sizes relate? How do the sides relate to one another? They're what? What's that word we're looking for? We're looking for the sides are what? The sides are in proportion. They're proportionally related here. Okay, so this means if I have a diagram like this, okay, if I have a diagram like this, this is angle A, that's angle D. If I knew that angle A and angle D were congruent, okay, were congruent, that's not going to be enough, right? That's not going to be enough to prove that these two triangles are similar, okay? Because what if this angle here and that angle here, and pretend this is like an obtuse angle here, right? Angle B, right? These aren't drawn to scale, let's pretend. Angle B is an obtuse angle. This is like an acute angle here. That clearly wouldn't be enough to prove that the two triangles are similar, right? This would go out like this would go down like this, they'd be different shapes, okay? So it turns out we just need one of these angles to be congruent because if we knew stuff about their sides, we'd be able to deduce that, yes, they'd have to be similar, okay? So their sides here would have to be in proportion. So this angle and this is angle D right here, they're congruent to one another. The sides that would include, okay, include angle A and angle D is this here, right? AB and AC include angle A. Why do those two sides include angle A? Well, angle A is two of the sides of angle A. Here is AB. And AC, okay? BC is opposite angle A, so BC does not include angle A, right? BA, CA, right? That's part of CA and BA is angle A, right? Is angle A. So these are the sides that include. This is called the included angle for sides AB and AC. This here, D, angle D, is the included angle for DE and DF, okay? So I think those are the ones that maybe we're thinking about here as we kind of talk about what we're going to need to prove in this one here. So let's check this one out. So this is what we're going to prove. I wanted to put it in front of you here because let's take this here. Let's try to take these words and turn it into, well, I showed you a diagram you could potentially use, but let's talk about like what's our opening premises here, right? That's at the part after the if. And then we want to prove that the triangles are similar. That's the easy part here. So question, right? If I'm going to try to prove the SAS similarity theorem, well, I got to have two angles in common. That's easy, right? SA, the angles are congruent. Sides are what? In proportion, okay? So what's given to me, I have angles being congruent and then sides being in proportion. So what's the other thing that's going to be given to us here? As then we're going to deduce what's going to follow from that is that the two set triangles are similar, okay? What do I need here? What do I need here? What's my other premise here? Well, sides are in proportion. Which sides? Somebody tell me, okay? They're going to have a common ratio, right? We don't know what the ratio is, but we're going to relate what side to what side and what side to what side, okay? Let's see here. Well, we're going to relate the sides that include angle A. So we're going to need A listed in either of the sides here. This is triangle ABC. So we're going to have AB and AC, right? AB and AC would include angle A, right? Because the end point of point A on AB and end point of point A on AC, that would be the vertex of angle A. So we would know that they would get included, okay? So AB would go to what? DE. AC would go to DF, right? And so we're talking about D over there here. Okay, so check it out here. I think that's what I said, right? This is what I said here, but this is the way we're going to prove this one here, okay? Is that we're going to take this, we have two congruent angles, one angle congruent to another angle, and what's going to be given to us is that AB to DE is going to be, so this here, this side to that side is going to be in a common ratio with AC and DF, okay? So if this is a 3 to 4 ratio right here, and we knew this was 5, is that a little bit hard? This is 6, let's say this is 6, then this would be 8, okay? Then this would be 8 here. So that would be enough to prove, and we'll prove it in a second, but if I knew that, if I knew this is in a 3 to 4 ratio, this is in a 6 to 8 ratio, then those they be in proportion with one another and that their included angles are congruent, that would be enough to deduce that these two triangles are congruent. Once we prove this, once we prove the SAS similarity theorem. Okay, you follow me with this one here? I don't know. I'm just trying to say a lot, get a lot in front of you so you can think about it and really tie things together as we go through. Okay, so now we get into the weeds, guys. We get into the weeds right now. You thought you were in the weeds already, but now we're totally in the weeds because we want to prove this for you here. This isn't just a postulate. Okay, we can prove this for you right now. So check it out. Let's get it up in front of you here. Of course, first step of a proof is almost always listing your given premises. Here, I'm doing teacher move right here. Notice this. I'm going to start just with the angles being congruent because that's what I'm going to talk about first as I prove this one for you here. Okay? So you might be thinking at this point, well, how am I going to prove, right? If I have to prove the SAS similarity theorem, how can I prove this? Because I don't have very many ways, right, to prove figures are congruent. Okay, what I can do to prove figures are congruent is I can prove all angles are congruent and all sides are in proportion. Okay, but the problem is I only have those sides that are in proportion. That's it. I don't know BC to EF is giving me in that same 3-to-4 ratio, or whatever the common ratio is between AB to DE and AC to DF. I don't know that. I'm going to try to prove that now. Okay, so, and I also don't know if angle B is congruent to angle E or angle C is congruent to angle F. So anyways, this might be pretty hard. So the way that I would go, my mind would go to it, I'm probably not going to use definition of similarity to help me right away at least. What I'm going to do is maybe think about how I can use AA here. AA. Well, this is a little tough. This angle is congruent to that angle, right? Because AA is the other way I can prove similar triangles at this point here. Angle B is, we don't know. Angle C and angle F, we don't know. So it turns out the way this gets done here, and I would never expect anybody to figure this out. I couldn't figure this one out here, but it's written about in the book because somebody figured it out and published it in a book, right? That's part of the glory you have as a geometer out there, mathematicians. If you discover things, you can put them in books. And everybody's like, oh, that's cool how that works. The key to doing this one here is introducing an auxiliary set. I'm going to build a congruent triangle over here. Triangle ABC is going to be congruent to another triangle over here. And if you're congruent here, right, this large triangle DEF would be similar to another triangle I'm going to create over here. And because these are congruent, right, they'd be similar to each other. And then, right, I would know that AB is similar to whatever triangle I create here. And DEF, right, which is the large angle here, is similar to, all three of them will be so similar here. So we're going to use the transitive property of similarity. Anyways, let's get into it so we can check it out here. Let's introduce our auxiliary set. So they just, like, if you look at the textbook, they tell you this is the proof. Think about it this way. I'm going to take it through with you guys. I think it's hard to read these ones. It's even hard to follow along somebody's reasoning, instructor's reasoning in this situation. But I'm still going to try to bring it through with you guys. So here's the auxiliary set you would introduce. Draw XY on triangle DEF such that DX equals AB and XY, segment XY, is parallel to EF. Whoa, that's a lot going on right here, okay? So maybe we should show it. Maybe we should think about this. Let's do this here. Draw XY on triangle DEF such that DX, okay, so wait, so AB here is going to equal DX over here, okay? We're going to basically copy that length, move it over here, and then this will be point X down here, and we'll draw a parallel to EF here. That's going to intersect this other side at point F. And if I did that, yeah, okay, if I did that, and I'm allowed to do that, we'll talk about the reasoning in a second. But if I do that, I'm going to create some congruent triangles here. Okay, let's check it out, and we'll prove that they're congruent in a second. All right, so I just drew that here. Did you just see what that was? Should we do it again? Okay, check it out here. I'm going to take my pen, or I take my compass, right? Swing it, copy AB, move it over to the other side here, so I'm copy that distance, and then I'm going to take my straight edge and copy, right, construct a parallel to segment DF, and if I have that there, I'm going to have triangle ABC. I'm going to prove that that's congruent to triangle DXC. We'll get to that in a second, okay? So step 2, though, we need to figure out the justification for that because there's a lot going on there. First of all, we drew XY on triangle DEF such that DX equaled AB. Why was I allowed to do that? How am I allowed to copy a particular distance, a specific distance? So I'm copying distance AB, okay, over here so that we have dx equals AB, right? That's where I'm plotting point X. Okay, the reason for that is the ruler postulate. Every segment has a real length to it, a real number length to it. And so if you're real number length, right, you can duplicate those, right? Numbers can be moved other places, okay? Then I also, right, through that point X, I drew a parallel to EF, okay? And I'm allowed to do that because through one point outside a line, there's exactly one parallel to that given line here, okay? So 2 auxiliary sets reasons. I know these auxiliary sets are tough, right? Because there's no section dedicated to auxiliary sets, but there are about 5 or 6 different auxiliary sets of lines or points that you're allowed to put in here. Okay, so ruler postulate, we're allowed to plot point X, which was exactly distance AB away from point D. That was justified through ruler postulate. And secondly, once we have point X, we're allowed to draw that parallel to line EF, because through a point, right, here's this point right here, outside a line, with the line being EF here, there's exactly one parallel we can draw through that point. Okay, you still with me? You still with me? I know that's a lot, right? These auxiliary sets pretty tough. But hey, check back on that document. Remember that document I shared last week? It was like 9 pages long that a mystery writer wrote about? Pretty much everything we've done. There's a little section there on auxiliary sets that perhaps you could brush up on and figure out how you can add things to diagrams. Auxiliary sets are just things you add to diagrams in order to help you complete a proof. Okay, so let's do this. The fun stuff begins. Let's actually prove the left triangle ABC is congruent to triangle DXY. And that's going to help us because DXY is going to be similar to DEF, and then they're all similar to one another. We got the SAS similarity theorem proven. Anyways, I'm getting ahead of myself here. First thing I want to do, okay, so it looks like I'm proving the similarity factor, okay? Because this is parallel to that. We've seen this. We saw this in the AA section. DXY is definitely going to be similar to DEF. And here we have one thing that's going to help us. Angle DXY is congruent to angle DEF. And why is that? Well, these are parallel lines. So if we have two parallel lines cut by a transversal, then hey, these are corresponding, right? Corresponding. Here's our transversal, and this is in the top right position, right? The transversal and the two parallel lines here, so they're in corresponding places. That means that we got to be congruent. Two parallel lines cut by a transversal, then corresponding angles are congruent. So that's good. Now, is this enough to prove that triangle DXY and triangle DEF are similar? Well, we have an angle there. We have an angle there. Oops, I should have put 2 tick marks down. My bad. We have this angle here and that angle here. Not to confuse you. These two angles are not congruent to those 2 angles here. Anyways, sorry for the confusion there. But hey, angle D is congruent to itself. So check it out here. Oh, I missed that as a step. I should have had that as a step in here. I should have said that angle D is congruent to itself. So I might put that in here up top here. I missed that as a step. You're seeing the rest of the proof here, but I should have done this. Angle D, so I can actually get this through AA. Because here I just had one, and you're just like, Mr. Ford, why are you doing this? 3A, and it's here. Ugh, what a mess. What a mess. Okay, so this is messy. I missed this step here because I wanted to prove, again, DXY similar to DEF. I just proven those two angles congruent to one another. But hey, I wanted to point this out here too. I never said that that angle was congruent to itself. Okay, I needed to do that because my next step of the proof is saying that triangle DXY is similar to triangle DEF. Reason? Well, the only reason that we have, the only shortcut we have so far, which is the AA similarity postulate. Remember, we're trying to prove SAS similarity theorem, okay? We haven't even talked about the proportion sides that we have here, proportional sides we have here, okay? So I missed that. Sorry about that. It's getting even more confusing than it needs to, but that's part of my job is to show you how confusing some of this stuff can be and asking you guys to dig deep, right? Dig deep here, okay? So those two triangles are similar, but hey, check it out. This triangle here, DXY, I can prove is congruent to ABC. We'll maybe get to that in a second here, but let's check it out. Let's introduce this. So this next step is very confusing as well. Check it out. It's very confusing. So I want to introduce the whole proportionality thing right here because check it out. Boom. Let's go ahead and drop it in here. Statement 5 here I'm going to say this, AB over DE equals AC over DF. That is actually the given premise. Okay, that's the given premise right here, is that I have that. And with my given premise beyond that, step 4 is allowing me to say this right here, that dx to de is in a common ratio with dy to df, okay, because of definition of similarity. So maybe put this one in here. Given is this. So here I'm using this given premise. Remember, I saved that from the beginning. Here's definition of similarity, right? Well, I did all this work to prove that triangle DXY is similar to triangle DEF. So, hey, I can similarly set up that this left side here to this left side here and this right side here to this right side over here, they would be in a common ratio. But wait a second, DX to DE and dy to df also in a common ratio from definition of similarity. But wait a second, which sides am I using between both these proportions? Look at this. In the denominator here, I have de. Denominator here, I have df. Here, I have de. Here, I have df. So these ratios here, okay, what we have here, and this ratio here, AB to DE, AC to DF, okay, they would equal each other here. But here, DX actually equals DE. Actually equals AB, okay? Where did I get that? Well, that's how I drew the sides. Look at this here. This is identical triangles to that one over here, okay? Because this side is the same, okay? And this is an AB to DE ratio. This is an a DX to DE ratio, okay? DX to DE ratio. Those are the same ratios because AB equals DX. That's how I drew it. I drew this point X down here to get that distance to be that distance here. So the ratios that are given to us, right, the sides that are in proportion, we have built other identical proportions here, right? The identical proportion here, DX is the same thing as AB, okay? And because this ratio is the same, DX over DE is the same as AB over DE, that would mean that DY over DF would be the same as AC over DF. Very confusing, very confusing. Look into it. See if you can follow my logic. I don't think everybody's going to follow me here, but the important thing is that this is getting proven for you. Okay, but so that means that AC has to be the same as DF here, okay? AB over DE, okay, that equals DX over DE because DX is the same thing as AB. Look at this over here, DX, same thing as DE. So that means that AC over DF also equals DX over DE. Those two are the same thing here. So we're kind of using this like transitivity and whatnot quite a bit here. AC over DF is going to have to equal DY over DF. Why does DY equal DF equal AC over DF? Well, dy over df equals dx over de, and dx equals ab, right? They're the same thing. Okay, so what we can deduce here is because df is in the denominator over here, and df is in the denominator over here, and ac over df is the same as dy over df, right? It's like if we have this 5 over 8, let's say that df is 8 and ac is 5, we have 5 over 8 here. This here is 8, what would dy have to be if they equaled each other? Well, dy also would have to equal 5, okay? So anyways, what I'm justifying here is that AC also equals dy, and that's important because, hey, next step here, we can finally say that triangle dxy, this one we built over here by introducing that auxiliary set, we didn't quite have enough to say that triangle dxy was congruent to triangle ABC, but now we do, right? Now we do because in the last step here, we established that AC must be equal to dy because dy to df would be the same as AC to df. So AC and dy would need to be the same, okay? So what we have here is SAS, okay? We have an SAS congruency thing here, right? Congruency thing here, and now, right, finally, okay, SAS congruency, a triangle ABC is congruent to triangle dxy, okay, that's great, but because we also knew previously that dxy was similar to def, so now we have this triangle congruent to that other triangle. What do we get for free? These two triangles are similar, right? That triangle is congruent to the triangle on top here. The triangle on top here is similar to the larger triangle down below. So if this is similar to that, right, because they're congruent, and that is similar to this other thing right here, okay, then this other thing here, DEF, must be similar to triangle ABC. And we've proven what we were trying to prove. And that is when we have an angle, right, in one triangle, congruent to an angle in another triangle, and side lengths in proportion, the two triangles need to be similar. And it's proven for you here, and yes, it's very confusing. Hooray, we got there. Triangle ABC has to be similar to triangle DEF, and that's through the transitive property of similarity. Steps 4 and 7. So here, I didn't even say that yet, right? Triangle DXY is similar to triangle ABC. That means triangle DXY is congruent to triangle ABC. We got that through SAS congruency. Therefore, I can say that triangle DXY is similar to triangle ABC. Other corresponding parts, other angles would be the same if they're congruent, and then AA similarity postulate. Or I can use definition of similarity to kind of get there. Really should have used AA similarity, but it's fine. We'll keep going here. All right, that was a lot, guys. Are you going to have to know how that proof works? No, but I wanted you to spend 10, 15 minutes with the pain of going through the proof with us. Well, we got it. We can take it now. Okay, so what triangle similarity shortcuts are there so far? Well, hey, we got AA. Just want to remind you, what have you learned so far? What are you going to learn here? We have the AA similarity postulate. Then we have the SAS similarity theorem. That's what we just proved a second ago, and head might be spinning from that proof, but that's all part of the geometry process, okay? SAS similarity theorem, so that means we got one more. Let's prove another shortcut. Shall we? We got one more to go. Let's do it. Question mark. Whew, another proof for us here. Writing it down. Let's do this. SAS similarity theorem. It's on now. Oh, it's a long lesson. It's a long lesson, isn't it? These are all long lessons. Let's do this here. All right, so here, theorem. Try to wake up. Get yourself here. Here we go. Theorem, SAS similarity theorem. If the sides of two triangles are in proportion, then the two triangles must be similar to one another. Easy. Write it down. Do it. All right. If the sides of two triangles are in proportion, then the two triangles are similar. Okay, what do we know about the angles? Well, we would be able to deduce if we had similar triangles that the angles would be congruent to one another, okay? But we don't. We're not starting with similar triangles. We're merely starting with two triangles whose side lengths are in proportion. We don't know anything about their angles, right? Don't know anything about the angles here, okay? We just know that, what here? Let's go ahead and write this one out here. We're trying to prove these true triangles are similar. We're not going to prove it through the SSS similarity theorem, okay? That'd be circular logic. We haven't proven the SSS similarity theorem. So we got to think about what we're given here. What's our opening premise here, okay? You look to the part after the if to figure out what your premise is of the theorem, and then the part after then, that's your conclusion. That's the thing you're trying to prove, okay? So you're trying to prove triangle ABC is similar to triangle DEF. Why? Well, you were given the side lengths are in proportion. That means all side lengths are in proportion. That means we got to set up how many ratios. This will be an extended proportion with 3 ratios here. So if we knew that AB to DE, that ratio is equal to AC to DF, and then finally that BC to DEF is in the same ratio. Here we got that one there. If we knew that, that's going to be enough, right? When we start doing problems, that's going to be enough to deduce right away those two triangles need to be similar to one another, okay? And that's what we're going to prove. We're going to prove that one right now. Let's do it. All right, statements, reasons. This one's a little bit easier than the last one. I think it's a fewer steps, and hopefully I didn't make a mistake by overlooking anything. But I think we'll get there. A little bit easier. It'll be a similar type of introducing an auxiliary set. We'll have to do that in this one here. All right, the side lengths are in proportion. We want to prove that these triangles need to be need to be similar to one another. Okay, so how can we do that? We can maybe work our way through the AA similarity theorem postulate. Maybe SAS similarity theorem. That might be involved, or some sort of congruency argument here. Okay, so let's try to see if we can work on it in this one. All right, here's how this proof works. We start with the side lengths in proportion. Okay, do we need to worry about that yet? No, because the proof's going to work the same way. I'm going to introduce what I think will be a congruent triangle. I'm trying to move ABC over here. Why can I do that? Well, again, I can measure out length AB, okay? And I can measure that out here, length AB down here, okay? If I had a compass, I'm missing my compass right now, okay? If I have a compass, I could swing the compass to figure out how long AB is, and then swing it to figure out how long AB is, copy it over here, get my point X, and then again, I'm gonna draw my parallel line, okay? Through that point X, I'm gonna draw a line parallel to segment EF, and that's gonna help me find, right? Again, this triangle on top, this triangle below are going to be similar to one another. And that's going to help us in this one here. Anyways, reasons for this. Let's go ahead and draw it on in again. Yoink. There we go. Reasons for this is, well, why am I allowed to copy segment length AB and move it over here? Well, any length is a real number. Where do we get that from? The ruler postulate tells us length AB is a real number distance, so I'm able to move that somewhere else if I want to. So that's ruler postulate. And again, through a point outside of a line, there's exactly one line parallel to a given line. That would justify the existence of a line XY parallel to EF and point X justifying its distance from point D as AB. That would be the ruler postulate. Okay, so that's all there is to that one here. All right, so what we're going to do in this one is, well, we're going to know, right? Because we already previously proved this freaking thing right here. Oh, wait, we didn't prove it here because I used angle D is congruent to itself. So we can still prove that triangle DXY is similar to triangle DEF. And maybe you have some ideas on how to do this. Why am I doing this? Well, I just drew a parallel line here. You should have seen this from last section. If I draw that parallel line through a triangle that's parallel to a third side, it's going to create two similar triangles, okay? That's not a theorem, right? It's just something you observed last time. You easily prove it, okay? But anyway, so we can make it a theorem if you wanted to, but I don't think we want to. So those are going to be similar to one another. And then you could actually prove this. We're going to prove that is, again, congruent to that guy up there. You might be wondering how. I might be wondering how. Wait a second. Where am I getting at this one? All right, so let's check this one out. First things first. Triangle DXY is similar to triangle DEF. Okay, here I did this in one fell swoop. How did I do that? Well, those guys right there. So I'm sort of condensing steps right now. How can I prove that triangle DXY is similar to DF? This is usually where I'd ask in class. Somebody tell me. Why? Well, these are parallel lines. What do we know about parallel lines? Well, they're corresponding angles here and here, and corresponding angles here and here. Those two pairs of corresponding angles congruent to one another. Very nice here, okay? So through two parallel lines cut by transversal, corresponding angles are congruent. And then, right, I can combine steps here. If I don't want to write it all out, I can say what? AA similarity postulate, okay? So DXY similar to DEF, those two triangles, because of the AA similarity postulate. And you'd have to justify, right, where you got that from, where you got the two angles. Here and here, here and here, because we have parallel lines cut by a transversal. And then those pairs of corresponding angles are congruent, okay? So we didn't need to well, I mean, we could have mentioned the reflexivity thing. Angle D is congruent to itself, but let's just not deal with that at all here, okay? So those are similar. Next step on the proof here, whoa, I'm setting up next step. So now I can mess with this. I have all these side lengths in proportion here, okay? That was my given premise, okay? Now I can set up another, check this out here. I can set up another proportion here. dx to de, and look at this here. This was AB to DE. This is dy to df. I can say that is a ratio equal to dx over de. Why? Well, there's similar triangles, so definition of similarity. And finally, I can say xy to ef would also have to be in that common ratio, okay? And the reason for that is a definition of similarity here, okay? We got this here. But look at this. We're going to make a conclusion here that's going to get us to this triangle top here being congruent to that triangle. Well, why? Because AB to DE, that is a common ratio in the first triangle, okay? The other triangle we had DX to DE is a common ratio between the second pair of two triangles that we had here, the one we created and then this large one at the beginning here. And what again do we know about AB and DX? AB equals DX. Check it out here. AB equals DX here. So AB over DE is the same ratio as DX over DE, okay? And that means BC over EF, same ratio as XY over EF. AC over DF is the same ratio as DY over DF here, okay? So the given proportions here from this triangle to this large triangle are the same as the proportions that we deduced from this triangle to that triangle, this triangle to that triangle. So here, if AB equals dx, AB over DE would equal XY over EF, but it also equals BC over EF. That means BC and XY have to be the same because they would form the same ratio with EF. Okay, AC and DY would have to be the same lengths because they would form the same ratio with DF down here. Okay, kind of confusing. Maybe you see it the second time. It's a little easier to see the second time through it, but it's a tough proof, right? Tough proof to kind of explain here. Okay, why is that important? Well, here, if you follow my logic around here, AB, well, we knew it had equal DC over here, because DX over here because the ruler postulate. That's how we drew it as such. But now we've deduced that AC and DY need to be the same. BC and XY need to be the same. So now we can say triangle. Okay, next up here, triangle ABC congruent to triangle DXY. This top triangle congruent to that triangle. Why? SSS. Okay, BC and XY we determined was the same the last step. AC, DY, determined those are the same in the last step as well here too. So those two triangles congruent through SSS. And then, right, since triangle DXY is similar to DEF, right, we got that earlier in step 3. DXY is similar to DEF. And ABC is congruent to DXY. So remember, triangle ABC, if it's congruent to triangle DXY, ABC would be similar to DXY. DXY is similar to DEF. Thus, finally, what we're trying to prove is that this triangle here is freaking similar to the larger triangle here. And if that triangle is similar to that triangle, and that triangle is similar to this other triangle, then the first and the third triangles must be similar to one another. Mic drop. Yes, I wish I did that in the classroom with you guys. Mic drop here. And the reason for that, transitive property of similarity. Because similarity is an equivalence relation. Oh man, so much to keep track of here. Like, why was I talking about equivalence relations at the beginning? Well, it was involved in the proof of that. The SSS similarity postulate here. Okay, what did I begin with here? Well, I began with all three side lengths were in proportion. What did I prove to you guys? What did I mic drop in with you? Well, then those two triangles needed to be similar to one another, okay, through a chain of reasoning that we had down here. Beautiful, right? Beautiful stuff. I love this. Don't you love it too? No, not really. Okay, so what triangle similarity shortcuts are there so far? Well, there are 3, and those are the last 2 proofs, only ones that need to be proven for you, because there's only 3 triangle similarity shortcuts that you need to be worried about and consumed with using this year, okay? So triangles can be similar if they have 2 angles that are congruent to one another, and one triangle congruent to another triangle. They're similar through the AA similarity postulate. They are similar if they have an SAS similarity correspondence. That means if one angle in one triangle is congruent to an angle in another triangle, and the sides that include the congruent angles are in a proportion with one another, that's enough to deduce that the two triangles are similar. And finally, the last one here. If we didn't know anything about the angles, but we knew that the three sides maintains the same ratio between the two triangles, that's enough to deduce right away. We can jump to it. Those triangles must be similar through the SSS similarity theorem, which says that if all sides are in proportion, you're good to go. You can just, right? Because I proved it for you, right? You have to prove it. I proved it for you in the last one here. Okay, these are the only triangle congruency shortcuts you will learn and need to worry about here. All right, next video, let's go ahead and do some classroom exercises for next video. I think this one's been long enough here. Hopefully you enjoyed rolling this out. Stick on with me, watch the next video, and then do your exit ticket afterwards. Bye.